they? Have you ever looked at a solar panel and wondered how it works? They just sit there, silent, no moving parts, no fuel, and yet somehow they magically create electricity. It looks simple, but under that glass is one of the most elegant pieces of applied physics that engineers use every single day. To really understand how solar panels work, we need to answer one fundamental question. How does something as simple as light turn into usable electric current that can power your home? First, let's get one thing straight. A solar panel is not a battery. It doesn't store energy. Think of it more like a pump. At its core, a solar panel is a semiconductor device that's been cleverly designed to push electrons in one direction. Most panels are made from silicon, the very same material used to make the chips in your computer and phone. Now, silicon is special. It's not a perfect conductor like copper, and it's not a perfect insulator like rubber. It's right in that sweet spot in between. That middle ground is the key to everything. In simple terms, silicon is fantastic at controlling electrons, instead of just letting them run wild wherever they want. Let's zoom in, way down to the atomic level. Inside a solid piece of silicon, electrons are normally locked in place, happily orbiting their atoms. But then, sunlight comes into the picture. Sunlight is made of tiny packets of energy called photons. When a photon from the sun hits the solar panel, it can transfer its energy to one of those locked-in electrons. If the photon has enough energy, it knocks the electron loose from its atom. This creates two things: a free electron that can now move around, and a hole where the electron used to be. This is called electron-hole pair generation. The simple version. Light gives electrons a swift kick, and now they're free and ready to move. But here's the catch. Random movement doesn't give us electricity. A bunch of electrons just bouncing around randomly inside the silicon won't power your TV. We need them all to move in the same direction. We need order. We need flow. And this is where the real genius of a solar panel comes in. It's a structure called a p-n junction. This is the heart of the whole operation. To create it, engineers take pure silicon and intentionally add tiny, controlled amounts of other elements. This process is called doping. They create two different types of silicon. First, there's N-type silicon, which is doped to have extra free-roaming electrons. Think of it as being negative. Then there's P-type silicon, which is doped to have extra holes, or spots where electrons are missing. Think of it as positive. When you press these two layers together, something amazing happens right at the boundary, where they meet. The extra electrons from the N side rush over to fill the holes on the P side. This movement of charge creates a powerful built-in electric field right at the junction. This field acts like a one-way street or a slide. It creates a permanent slope. Now, when sunlight hits the panel and knocks an electron loose, that electric field immediately grabs it and forces it to move in one specific direction, while the hole gets pushed in the opposite direction. That's the key. The p-n junction turns random movement into directed motion. So, now that we have electrons being pushed in a single direction, how does that become the electricity we can actually use? Well, once those electrons are pushed by the electric field, they want to keep moving. If you connect a wire from the N-type side to the P-type side, you create a complete circuit, an external path for them to follow. The electrons flow out of the panel, through the wire, powering whatever UV connected, like a light bulb or your phone charger, and then they flow back into the panel on the other side to complete the loop. That organized flow of electrons is exactly what electric current is. It's important to remember that solar panels produce direct current, or DC, and this current only flows while light is actively hitting the panel. No light means no photons to knock electrons loose, which means no electron flow and no current. It's a direct conversion of light into electricity happening in real time. Now, you've probably heard the terms current and voltage. We've talked about current, the flow of electrons. But what about voltage? The p-n junction doesn't just create a flow. It also creates voltage. Voltage is simply a measure of electrical pressure. Because the electric field separates the electrons and holes, it causes a buildup of negative charge on one side of the panel and positive charge on the other. This difference in charge is the voltage. It's the push that forces the current through your circuit. A single, tiny solar cell only produces about half a volt, which isn't very useful on its own. That's why solar panels are made of many cells wired together in series to add up their voltages and create a much higher, more useful voltage. As amazing as this technology is, solar panels aren't perfectly efficient. Engineers are constantly battling against the laws of physics to squeeze out every last drop of power. There are several reasons for this. For one, some photons from the sun don't have enough energy to knock an electron loose, so they just pass right through. Other photons have way too much energy. They knock an electron loose, but the extra energy is just wasted as heat. Another big issue is something called recombination, where a freed electron falls back into a hole before it can escape the panel and join the electric current. Plus, there is always some electrical resistance in the silicon and the metal wiring that causes a little bit of energy loss. That's why most commercial solar panels are around 20 to 25% efficient. This isn't a sign of bad engineering. It's just the physical limits of the materials we're working with. This also explains why things like angle, temperature, and shade are so important. The angle of the panel determines how many photons actually hit the surface directly. A panel facing straight at the sun captures the most light. Shade is simple. It blocks photons entirely, so that part of the panel stops producing power. And here's a surprising one: heat. You'd think solar panels love heat, but they actually work less efficiently when they get too hot. The extra heat makes the atoms in the silicon vibrate more, which increases the chances of electrons colliding and losing energy instead of flowing smoothly. That's why panels perform best in bright, direct sunlight on a cool, breezy day. So, the panel has done its job. It's rated DC electricity, but the outlets in your house use alternating current, or AC. So how does this power become usable? That's where the rest of the system comes in. An inverter is a crucial device that takes the DC electricity from the panels and converts it into the clean AC power that our appliances use. More advanced power electronics and grid synchronization systems make sure this AC power matches the frequency and voltage of the electrical grid perfectly. But no matter how complex the system gets, core physics always starts the same way. Light knocks an electron loose, an electric field gives it direction, and that directed flow becomes current. In the end, solar panels are a beautiful example of human ingenuity. They don't work because of complicated moving parts or by burning fuel. They work because engineers figured out how to use the fundamental properties of light and matter to command electrons to move. It's just physics, doing exactly what it's told, silently turning sunlight into power for all of us. Thanks for watching. If you found this interesting, don't forget to like and subscribe for more deep dives into how our world works.